for inviting us here. Thank you, all the IEEE guys who have taken time out of your day to come and see what we worked on throughout the year. For our project, we developed an electric powertrain for an electric formula car. My name is Ian Pasco. To my left is Marguerite Smith. To my right is Drew Beerlaw and Teddy Lee. We've got a list of items that we're going to share with you today about our project. Teddy's going to kick it off.
So FSAE is the Society of Automotive Engineers, and they host combustion engine and electric vehicle competitions for college students to compete in racing. We at Miami have a Baja team that competes in the combustion engine races, and that acts as a showcase for prospective students in the NME department. But with the trend towards electrification, the team was looking at starting the EV section of that racing, and they started that in 2022. And that's why our goal was to actually develop the powertrain for that electric vehicle. And then some of the constraints that we had to work around set by the FSAE rules was the max power draw of 80 kilowatts, and then the max voltage of 600 volts and 182 points on the vehicle. And then the FSAE also has technical tests that are conducted before the races. The electrical scrutineering consists of the paperwork and safety checks before the race starts, and then the tilt test where the vehicle's flipped to 45 degrees, make sure that doesn't have any faults, or the rain test where the vehicle's sprayed down from any possible angle to make sure that the water incorporated in the system doesn't create faults.
This diagram shows the architecture of an electric vehicle and is what we based our design off of when we first started. So some of the main components that we had to choose in terms of what specific brand we were going to use were the battery. We chose the Enapac BT6 cells, the battery management system, we chose Orion, the controller, just Cascadia, and the most important part to us is the motor, the MRAX 188. So why did we choose the MRAX 188? There's so many good options that other teams use. We were considering price, we were considering implementation ability into a future car, we were considering power to weight ratio, but most important to us ended up being the accessibility of acquiring that item.
Okay, so this is the schematic of how we wired the motor and inverter together. Motor is on the right, inverter on the left. You can see the three-phase cables going into the motor, and then there's a feedback loop with a resolver, and then controlling the inverter is two systems which work together. We have the throttle and brake pedal, which are essentially potentiometers, and then there's a series of enable switches that transfer the inverter between different modes, that being forward, reverse, and braking. And then lastly, on the left side of the schematic, there is a pre-charge circuit, which essentially protects the inverter and motor during operation. Okay, another thing that we had to determine in this project was the gear ratio. So how we did that, we used the formula on the bottom of the screen. And I really quick want to talk about how we selected the maximum RPM. We did some simulation early on and found that the fastest lap time came when we kept the motor out of the field weakening range. Field weakening for the MRAX 188 begins at 6,500 RPM, so we used that as our maximum value. Plugging all those in, we found that our gear, or the optimal gear ratio, was 1 to 3.
So one of the other major milestones we completed as part of this project was battery sizing. And so you can see to your left there's a picture of a sample FSAE car driving around a track, and that tells you where the car pulls higher or lower power. From there, we generated a plot of the instantaneous power draw of the car as it goes along the track, and that helped us determine our total energy requirement for the battery, which from that equation came out to about 7.3 kilowatt hours. And so with that, we were to calculate the specific battery parameters like voltage and capacity, So we use that equation on the top there with the max RPM mentioned earlier, and then the motor constant for RPM per volt. And with that, we got a battery voltage of around 330 volts. From there, we want to figure out how many battery cells to connect in series. And so we found that with a max voltage module of 4.04 volts, we wanted about 82 modules connected in series. And then last but not least, we wanted to figure out the capacity for each of those modules, how many battery cells to connect in parallel. And so we came out with about 91.5 watt hours to meet that total energy requirement. And you can see on your right there is the battery module for the BTC6 cells that we selected to meet that need.
So another aspect of the project was the cooling system. So we chose the liquid cooling version of the motor because one of the tests was the rain test. So this made sure that the components wouldn't fault in that scenario. So the radiator sizing, we used thermal calculations in a MATLAB to calculate the surface area that we needed of the forced air over it to make sure that we were getting sufficient cooling. And we divided that in half to get the size of each radiator that we wanted, because we wanted to put a radiator on each side. And then the pump sizing was based off the components' pressure limits and flow limits of the individual components. And the loop sensors that were included were flow sensor, pressure sensor, and temperature sensor. And that was just to make sure that we're able to check on those through the life cycle of the loop. And then the Arduino Pro Micro was chosen as the controller because it has a higher threshold and resistance to shock and vibration compared to other controllers.
So there's a lot of safety concerns when using and testing this high voltage equipment that we acquired. So our plan and our task was to create a preventative procedure for high voltage testing and safety, not just for the safety of our group of 4, but for the safety of the Red Rock Racing FSAE organization as a whole. And because we were able to create that, these students are now aware of the dangers of arc flash, regenerative braking in the shop, and other dangers like not using proper PPE. So once that's been presented to all the students, now that they're all aware, hopefully we can respond to any emergencies that occur in the best way possible and prevent them from happening at all.
All right, so as we finish up the project, towards the end of the semester, we want to connect the inverter and motor on a low voltage test bench and test that our motor is spinning as it should, as expected. Along with that, we want to have our liquid cooling system connected and completely ready to demonstrate. On top of that, we will be documenting the high voltage battery wiring as part of the ESF, or the electrical systems form. This is something that's required in all FSAE competitions, and this is being documented for future teams to implement, since as a first year team, we have not yet acquired our high voltage battery. And you can see to your right here is the cab assembly for the rear of the car, which includes the motor mounted on there. At this point, I'd like to open up to any questions. Thank you.